Welcome to this talk on techno-economic and sustainability evaluation of carbon capture, utilization, and sequestration alternatives. My name is Rafiqul Gani. I will be giving the talk together with contributions from Ms. Orakoch and Mr. Jagrapat from the Thai office for PSEfor Speed. Let me also, before the start, acknowledge the invitation from the organizing committees of the first Thailand National Chemical Engineering and Chemical Technology Conference 2022, focusing on decarbonization. Let me try to see if I can also move the screen. Okay. So, since decarbonization means a lot of different things to different people, let us first define what we mean. The goals of decarbonization can be measured in terms of CO2 released, in terms of resources used, in terms of temperature increase, and many more. Indirectly, also, it can be measured in terms of effects on climate change, availability of resources, uses and needs of products, and many more. Also in terms of the Sustainable Development Goals defined by the United Nations and many other ways. How to achieve these measures? Obviously, by reduction of CO2 emission, by reducing energy demand, utilize captured CO2, generate only the amount of CO2 that can be captured and utilized, look for integrated solutions, taking into account regional constraints, and many more. The means to achieve these goals would be integration of ideas, concepts to develop significantly better technologies than we have currently, use new conversion and or separation technologies that also will contribute, develop and use methods and tools that can give significantly better solutions than the solutions that we are currently using, and again, many more. We also need to take into account that within the period 2021 to 2050, if we want to keep the temperature increase to 1.5 degrees Celsius or less, we have to capture and utilize or sequestrate at least 754.09 gigatons of CO2. Out of these, 32% needs to be tackled by the industry. Besides capture and utilization and sequestration, the CO2 amount can also be reduced by other means. For example, improved design and operation of processes. So chemical processes by definition are energy intensive, and within chemical processes, distillation operations are the most energy intensive. The figure on the left you see is a distillation train that can be found in many petrochemical refinery plants, and they are the most energy consuming operations within those plants. So what can we do about the two distillation columns that are highlighted, which are among the highest energy consuming operations? We have a long-term solution, that is replace the distillation columns totally. However, that long-term solution is not yet available for use, so we can think of short-term solution. And short-term solution is to integrate or combine the existing distillation column with a small membrane operation, which is completely feasible, and combine them in such a way that the distillation column does not use the same amount of energy, and at the end of the membrane operation, we get the purity of the product that we are interested in. The rules for combining these two operations to get a hybrid scheme is combine the two techniques, that is distillation and membrane, such that each operate at their highest efficiency. Savings of up to 10 to 50% can be achieved depending on the separation that is being done. Considering that there are more than 200,000 distillation columns operating on Earth, the scope and significance would be very large if we can replace the existing distillation columns, not replace, but augment the existing distillation columns with a small membrane in a hybrid scheme because we would be making an immediate effect. With that, I will not go into much more details on improving the chemical process efficiencies, but go directly to the topic of capture, utilization, and sequestration. The first scenario I would like to highlight is capturing the CO2 from different sources, in this case, air and flue gas, that can come out from energy supplying process as well as energy demanding process. And then depending on the source of CO2, the capture technologies are different. The objective, of course, is to reduce the net CO2 emission. The question is, where is the real boundary of the system? What you see on the figure is a network of different alternatives that are possible to capture CO2 from air or from flue gas and get a purity of 90% or higher in the captured CO2, and then we have clean air. The network is showing that steps 1 to 4 are needed for the capture process, because the capture process may need more than one operation. And then step 5, which also needs more than one operation, but shown in a simplified way, that they are the utilization and sequestration alternatives. Steps 1 to 4 each indicate an operation or a network of operations, especially steps 2 and 3 and 4. And these steps are shown in a simple way with one box, but in principle, they are multiple alternatives within each. For example, chemical absorption or absorption by TSA, they may have multiple alternatives to perform that operation. So in principle, this figure shows possibility of a very large number of alternatives that can be applied if we have all the information that we need to do the calculations. So collecting all the information that we could find, we have calculated the total annualized cost, CO2 emission, and many more, just highlighting only a few of them. So we can calculate the operating cost, the capital cost, carbon footprint, net emission, and the objective is to create a technology table of capture technologies, highlighting the important measures. At the end of the analysis, we give a score to each technology. Scores of 1 and 2 indicate that even after the capture of the CO2, the net CO2 emission is still positive because there are indirect CO2 emissions. Whereas scores 3 and 4 show that the net CO2 emission is actually negative. 2 and 3 are close to 0. So with this now, we can do calculations, and that is calculations of mass energy balance, sizing of the equipment, energy evaluation, all of those. And let me show you some examples first. The DSC process that captures the CO2 from air, but needs energy from an energy supplying process. And we can do the calculation for this, and the boundary is shown. However, if instead of just energy supplying process that can be non-renewable, we can also use other sources of energy, then this becomes an integrated DSC, and the boundary is still the same, but now the net CO2 emission by definition would be lower. And the third one is we combine the air-based DSC with the flue gas-based separation. And the reason we do that is that the air is much smaller, the flue gas contains much more CO2, and the flow rate is also bigger. So we can combine the DSC and the flue gas in such a way that we still get net zero CO2. And we have the scheme for doing this, and the figure shows the different ways to capture the mixed air flue gas stream, and also recycle if necessary if we want to move from one alternative to another. So, and an example of this is shown here, where the DSE is a multi-stage membrane and the flue gas is absorption. And we need multi-stage membrane because the exit permeate CO2 composition that we need cannot be achieved in one stage because of pressure differences. So, and we also combine here not only the non-renewable energy source, but also the renewable energy source. And the different alternatives are shown. The utilization and sequestration are not considered here. The objective is still to achieve net negative CO2 emission. We have generated schemes or technologies for more than 100 alternatives, and then we have classified them according to the different scores. And each of them we have the corresponding detailed calculations through which we have given the score. So the first set is scores of 1 and 2, and you can see that many well-known processes like membrane-based physical adsorption, ionic liquid-based chemisorption, solid and liquid, these are found to be positive or scores of 1 and 2. And an example of the technology table is shown here, only for a few of the calculated values, but there are more than 30 columns of calculated results for each technology. Then we can show that by doing an integration, we can convert technologies of 1 and 2 to 3 or 4. And here is an example of a physical adsorption process that is having score 4, but there is also chemisorption liquid and chemisorption with MOF and many more. And here is an example of integrated DSE technologies combined with flue gas with score 4. And one thing to note here is that membrane operation, which was originally 1 or 2, now combined with physical absorption, becomes a 4 score technology. Similarly, physical adsorption with zeolite RWY type combined with physical adsorption becomes a score 4 alternative. So integration is necessary if we actually want to have a win-win situation. So that was scenario 1, only about capturing. Now we want to keep the capturing that we have talked about before, and then use the captured CO2 together with the process to make something else. So here is utilization. And so what we are doing is combining energy demanding technologies, that is the process, with energy supplying technologies, that is the flue gas, and other CO2 that is coming out in the air and flue gas. So combining all of this together, we want to find new innovative solutions that give us negative CO2. Here is an example, and similar examples can be found. Many other examples can be found like this. We captured the CO2. We use the captured CO2 with available hydrogen generated in different ways to make methanol. Then we use the methanol with additional CO2 to make dimethyl ether, and there is unused CO2. In addition to dimethyl ether, we can also make dimethyl carbonate, succinic acid, and many more. The table shows the results, overall results, but it's important to highlight the row at the bottom where it shows the global CO2 reduction. And we can see that we can get negative CO2 emission for dimethyl ether, for dimethyl carbonate, for succinic acid and others. But is that good enough? Actually, it is not, because the amount of carbon atoms in CO2 stream that we have captured is much, much bigger than the amount of CO2, total amount of CO2, or the total amount of carbon in dimethyl ether, dimethyl carbonate, succinic acid, etc., other products. So which means that without sequestration of the remaining CO2, the impact on GWP will be very low. Sequestration, in my opinion, is not a long-term solution, But until a better alternative is found, that is a good way, at least temporarily, to get rid of the CO2 out of the circulation. So that is scenario 2. And we have seen that scenario 1 and 2 is not enough to achieve the decarbonization that we need to achieve. And the figure on the screen shows the technology up to now. We have the capture of the CO2, we have the utilization of the CO2. What we need also is to integrate the energy networks, renewable, non-renewable, as well as the water network, to obtain a total integrated system where the CO2 emission will be less than 100 parts per million. The net CO2 emission will be negative. This will be a totally integrated system with self-sufficient or self-sufficiency for energy, minimum need for fresh water, products that we need, and so on. Can we achieve this, or can this very complex, large problem be solved? What I would say is that we have solved one process, at least one example, and here is the details of it. We have the process that is with the green parts. Then we combine this process with the conversion technologies for energy. That will be the energy supplying process. Our original process is the energy demanding process. And whatever CO2 is generated from the energy supplying process will be captured and utilized by our process. Similarly, we will do for the water, different resources, and we will recycle the used water to minimize the need for the fresh water. So objective here is to determine a sustainable network that is networks, sub-networks within the total network, and we optimize all of them together so that we have negative CO2 emission that is economically feasible, safe to operate, and so on. We have published this example to convert biomass to CO2 and plus CO2 to xylitol, achieving net CO2 zero emission with economic feasibility, safe operation, and so on under uncertainty. We have the detailed conceptual design calculations showing the results for all the different parts together and also different scenarios. If you're interested in any of them, also of any process, new process that can be integrated in such a manner, we would be happy to help you to do this. So finally, in conclusion, I would just like to show some challenges. On Earth, we have different resources that are not uniformly distributed, but we need these resources to convert them into the products that we need for our sustainability. So the challenge is how to define the products to make, how to identify the raw materials that can be used, how to find a process that can manufacture the product in a sustainable manner, and many more. The decisions we make with respect to which product to make, which resources to use, which processes to select to convert the raw material to products, etc., have consequences, as you see with the figure on the left, because all of these will affect water, environment, health, energy, food, and these are also integrated. So that is the challenge. And also we have to think of that we have a growing population on Earth, and by 2050, the global GWP will have to increase. That will require increased capacity for most commodities, which will require more energy, more electricity, more water, and more release of greenhouse gases. So the challenge is how to address the interactions of energy, water, environment, health, food for a growing population. Finally, I would like to propose this challenge for chemical, biochemical, and related disciplines. And the challenge is how to flatten the effect capacity curve, which I will show you through decarbonization and other means, so that the 17 Sustainable Development Goals can be achieved. What I mean by effect capacity curve is this. I think many of you probably would be familiar with this. After the pandemic, effect X could be global warming potential, could be CO2 emission, could be temperature increase, could be number of infections due to COVID-19, could be number of deaths due to COVID-19. The gray curve is the business as usual if we do not do anything. The green curve is if we do something and we flatten the gray curve to be below the dashed line, which is the Earth's capacity to endure a specific effect. So that means there are many curves like this, and we have to flatten all of them to be below the effect, below the capacity for Earth. And if we can achieve that, then we will achieve one of the 17 or more, one or more of the 17 sustainable development goals. And decarbonization has a big role to play in that. With this, I finish my talk, and I thank you for your attention and interest, and I would be